Hello, my name is Oscar Nierstrauss. Today I'd like to show you how to find things in GT. Let's start with Spotter, a tool that allows you to search for entities by name. For example, we can search for string, which will find us the string class and open a coder for us. However, we can also use Spotter to dive in and express more detailed queries. Spotter shows us classes, packages, and methods that match the string query. We can also dive into the string class within Spotter. Now we see instance methods, inherited methods, and other features specific to the string class. We can now express queries specific to this context. If we type as B, we see only the matching methods. We see that as byte array sends self-subclass responsibility. This means that the method is abstract. If we search for subclass responsibility, we see that there is just one implementer, but over 4,000 senders. If we dive into the senders and query for string, we see that it has 4 abstract methods. We can also quickly find senders and implementers of messages using keyboard shortcuts. Command N for senders and Command M for implementers. From the coder view of the string as byte array method, we can position the mouse in any message and type Command M to find the implementers. For example, we can quickly see that there is just one method that implements subclass responsibility, and there are many senders. Searching for senders is especially useful to understand how to use an API. For example, if we ask for senders of all ranges of regex matches, we immediately find a test that illustrates its usage. What if we are looking for something more complex, like all the abstract methods within a package? In this case, GT queries are useful. For example, this query returns all the senders of the subclass responsibility message. In the metrics view, we can see that there are over 4,000 abstract methods in the system. Suppose we just want to find the abstract methods in the string class. In that case, we can compose this query as follows. Here we apply a filter to the previous query, restricting the scope of the result to the string class. As expected, we find just 4 abstract methods. If instead we want to find all the abstract methods in classes within all the collection packages, we can specify a different filter. To answer certain questions about the code, you may have to directly query the classes and methods of the system. Suppose, for example, we have learned that classes respond to the message is abstract. For example, the collection class is abstract. Curiously, string is not abstract, though its byte array method is. We can easily find all abstract classes within a hierarchy by asking the root class for all classes within its hierarchy and selecting those that respond positively to the isAbstract message. We already saw that we can find the abstract methods of a class by asking for those that send subclass responsibility. Alternatively, we can just select those that respond true to the isAbstract message. So now we can query a hierarchy for all its classes that have at least one abstract method. Now we can ask the interesting question, which classes are not flagged as abstract but do have abstract methods? There are several collection classes that really should be abstract, including string. And there are over 1,000 in the system as a whole, suggesting we may be wise not to trust the isAbstract message for classes. Sometimes you are looking for a method that does something you want, but you have no idea what message to send. In this case, the MethodFinder is handy. For example, suppose we don't remember how to concatenate 2 strings or 2 collections. To find this, we just create a new instance of MethodFinder and send it find methods by example input and expected result. In this case, we are looking for a message to send to the string foo with argument bar, returning foobar. The answer we are looking for is the comma operator, which works for any kind of collection, not just strings. Sometimes you see a view of an object and wonder, how was that computed? If we explore the hello string, we find that individual characters have a Unicode representation. By Option or Alt-clicking on the Details tab, we can see the code that generates this view. We can copy-paste the relevant code to the playground of the character to verify that this code does what we expect. This also works for buttons. For example, we can explore the code of the Inspect Object in a New Window button, and we can verify that it works. Sometimes you want to find code behind the UI, but you don't know where to start looking. In this case, you can drill into the UI and explore the tree of elements. We can increase or decrease the font size of a letter page by typing Command equals or Command minus, but how does it work? By holding the Shift, Control, and Opt keys while clicking on a UI element, we can explore it. We can now explore the tree of elements. We can inspect one of these and see in the Shortcuts view the current key bindings. We see that self-increase font size is sent to the LePage tool content tree element instance. We can try out the code to verify it. You'll find more GT and 7-minute videos on our YouTube channel, or you can explore GT by downloading it from gtoolkit.com. Thanks for listening.